Polynomial functions can be degree 0, a constant, degree 1, linear, degree 2, quadratic, degree 3, cubic, and so on. The behavior of the graphs of polynomial functions at different degrees can suggest what type of polynomial will best fit a particular dataset. You can use a graphing calculator to help you find functions that model the data in the table shown here. Enter the data into calculator lists L1 and L2, or a table on Desmos, and use three different regressions: linear regression, quadratic regression, and cubic regression. Graph each regression function and the scatterplot of the data in the same window. First, a linear regression, or the calculator feature linreg, graphed at the left, a straight line attempting to model the data. Next, quadrag, a quadratic regression using the quadrag feature of the calculator, a parabola attempting to best model the data. And finally, cubic reg, a cubic regression model best fitting the data. Fits very nicely. For this data, a cubic function appears to be a perfect fit. Take note, key concept, the n+1 point principle. For any set of n+1 points in the coordinate plane that passes the vertical line test, there is a unique polynomial of degree at most n that fits the points perfectly. This principle confirms that any 2 points determine a unique line. 3 points that are not on a line determine a unique parabola. 4 points that are not on a line or a parabola determine a unique cubic, and so forth. Problem 1. Using a polynomial function to model data. What polynomial function has a graph that passes through the 4 points, 0, -3, 1, -1, 2, 5, and -1, -7? Well, step 1. By the n+1 point principle, there is a cubic polynomial, its standard form y equals ax cubed plus bx squared plus cx plus d, that fits the points perfectly. So we'll substitute the x and y values of the 4 points to get 4 linear equations in 4 unknowns. First, for the point 0, -3, we'll substitute -3 for our output, 0 for our input, and see that -3 will equal a, our leading coefficient, times 0 cubed, plus b, our second coefficient, our quadratic term coefficient, b times 0 squared, plus c, the coefficient of our linear term, times 0, plus d, our constant. That leads us to the equation 0 times a plus 0 times b plus 0 times c plus 1d equals -3. Therefore, d equals -3. For the point 1, -1, again substituting and simplifying, we find 1a plus 1b plus 1c plus 1d equals -1. Substituting 2 and 5 from the ordered pair 2, 5, we arrive at the equation 8a plus 4b plus 2c plus 1d equals 5. And finally, our fourth point, -1, -7, leads to an equation, -1a plus 1b minus 1c plus 1d equals -7. 4 equations and 4 unknowns. Step 2. Write the system in augmented matrix form. Use the RREF, or reduced row echelon form function, to find the coefficient values a, b, c, and d. If you recall, our first equation revealed a d value of -3, which could then be substituted into the 3 remaining equations to eliminate the 4th variable and create a system of 3 equations and 3 unknowns, which could then be solved with elimination, substitution, graphing, or matrices. Continuing with matrices and a graphing calculator or matrix calculator online, step 3. A equals 1, b equals -1, c equals 2, and d equals -3. So the polynomial function is y equals x cubed, substituting a equals 1 in as our leading coefficient, minus x squared, b was -1, plus 2x, c is 2, minus 3, d was -3. And we can check. We'll use cubic reg, or a cubic regression model on Desmos with the 4 given points. On a graphing calculator, cubic reg, y equals ax cubed plus bx squared plus cx plus d. Our values a, b, c, and d check out. And with the graph, we have a perfect fit. The solution checks. Your turn. What polynomial function has a graph that passes through the 4 points -2, 1, 0, 5, 2, 9, and 3, 36?